So it says, Scarlett, I'm having a hard time with C. I'd like for you to simply be walked through this problem. All right, so we got this word problem, but unfortunately, if I'm going to go through or at least get to C, I got to be able to kind of go through all of the steps here. So let's first go and talk about the formula for a decay. Now, we're specifically have the half-life, but we'll talk about how that comes into. So if we're talking about a mass and we're talking about decaying mass, in this in particular case, we have a half-life. We are going to use this formula, which is going to be, come on, m of t equals m of 0 e to the k t. All right, so that's going to be when m of t is going to equal the mass at time t, where you're going to have m of 0 is going to be the initial mass, and t is obviously going to be the time, and k is going to be what we call our decay constant. All right, so the decay constant is always going to matter on like how fast and it is decaying in that regard. So when we have a half-life, we're going to have a certain constant. So that's what I want to, man, it is not liking this live stream. So that's going to be a decay. K is going to be equal my decay constant. Okay, so how do we be able to identify K? Well, in this case, we have the half-life, right? So that's really important because if we have a half-life, that means let's just for whatever time t, well, in this case, it has a half-life of 30 seconds. So let's go and identify this portion here real quick. So if I have a half-life, that means it doesn't matter whatever the mass is, what the initial mass is. Let's say the initial mass is going to be 2. Then after the half-life, the final mass would be 1, right? So I could use like 1 and 2 because obviously I don't want to use like 36 and 72, right? Let's keep the numbers easy. Then we have E. We have our constant that we do not know. And then we have T, which represents the time for the half-life, which in this case is going to be 30 seconds. All right, so now let's go ahead and solve for K. So to go ahead and do that, I'm going to divide by 2. I get 1/2 equals E to the K, or 30K. Let's write the 30 in front. Now to go ahead and solve for the K, I got to get rid of the E raised to that power. So I'm going to take the natural logarithm on both sides. That's going to get rid of that E over there on the right-hand side. And now I'm going to be left with a ln of 1/2 equals, a 30K. And then in this case, I could write it like, I could just keep that in there. But just remember that you could also do this as ln of 2 raised to the negative first power, and then use your rules of logarithms to bring that negative down in front, right? So therefore, I can go ahead and solve for K, which is a negative ln of 2 divided by 30 equals K. So that is going to be our constant because we have a lot of variables going on here, right? We have our mass at time t, we have our initial mass, we have time, and then we have our decay constant. So we have identified what our decay constant is through the half-life at 30 seconds. And now let's get into the word problem. So it says, suppose you have a 300-gram sample. All right, so that is going to be our initial mass. Find the formula for the mass remaining after t seconds. Okay, so we don't know what it's going to be after t seconds. So that's going to be, let's do this. So let's do A. So I have m of t, which we do not know. All right, so it just says find the formula, right? So we're not actually going to figure out. So we don't know what m of t is. We know the initial amount is going to be 300, and that's going to be E raised. Now I'm going to use this formula for my K, right? So it's going to be a negative ln of 2 divided by 30, and then times T, which in this case is, we are going to have find the formula for the mass remaining after t seconds. There you go. So yeah, that's going to be your input, and that'd be then. So that would be your formula for in that case. Now, if we want to be able to figure out for B, how much of the sample remains after 200 seconds, well, now we have our time, right? So for B, that's going to be m of 200. And that's going to be 300 e raised to the negative ln of 2 divided by 30 times a 200. All right, now I did find my calculator that my students, or not my students, my daughters stole from me. So I'm going to go ahead and type this in and see what we get. So I'm going to do that negative ln of 2 divided by 30 times that by 200. And then I'll do e raised to that answer and then multiply that by 300. And therefore, after 200 seconds, I am getting a 2.952. All right, and I'm just going to leave that truncated in that regard. So that's going to be how much of their mass is remaining after 200 seconds. Now, Scarlett, to your final part here, which is going to be for C. After how long will only 20 grams remain? So, yeah, I know. 20 grams remain. So that is going to be our final. So now we're going to be looking for the initial. So if we say, all right, so for 20 grams, we're looking, that's going to be our final amount. Now we don't know what our initial is. So that's going to be M of 0. That's what we're going to go ahead and try to find, right? After how long will only 20 grams remain? No, sorry, we need to solve for T. We already know what the initial amount is, 300. Sorry about that. So that one's going to be 300. And then we have E raised to this crazy thing, negative ln of 2 divided by 30 times T. Okay, so now we need to go ahead and solve for T. So to go ahead and do that, I need to isolate the exponential. Before I can take the log, I got to go ahead and get rid of this 300. So I'm going to divide by 300 on both sides. I can divide out those zeros. And then I have 2 over 30, which is going to be a 1 over 15. Excuse me. So I have a ln of 1 over a 15, which notice, just like I did over here, notice I can rewrite that as 15 to the negative first power and then rewrite the negative in front. So ln of 1 over 15, which really can be negative ln of 15. And that's going to be equal to this E negative ln of 2 over 30 times T. All right. So again, to get rid of this, or to get the powers off of our, to get the powers off of being a power of ln or of E. Wait a minute. What did I do? Oh, I'm jumping ahead of myself. That's just 1 over 15, right? That reduces to 1 over 15. Now we'll go ahead and take the ln of both sides. Sorry, I was like thinking ahead of myself. So now, rather than rewriting this as ln of 1 over 15, I'm going to rewrite this as a negative ln of 15. Okay, so hopefully I'm not jumping ahead for you. You can see we did that exact same thing over here, right? I'm just rewriting the 15 raised to the negative first power and then bringing that down in front. And then over here, I'm going to be left with a negative ln of 2 over 30t. Well, how do we solve for t? We got to undo what's happening to t. Well, what is happening to t? It's being multiplied by negative ln of 2 divided by 30. So I'm going to divide by negative ln of 2 divided by 30. And this is not really fun writing with this stylus, negative ln of 2 divided by 30. So now I can see that my negatives are going to go to add 0. And then also, I don't really want to rewrite this as a ln of 15 divided by ln of 2 divided by 30, right? If I wanted to get this 30 off the denominator, if I multiplied by 30 on the top and the bottom, those would divide out. And now I would get a final expression of t is equal to a 30 ln of 15 divided by a ln of 2. That's a lot easier for me to be able to go ahead and compute, right? So I'm going to rewrite it that way. And again, as long as you multiply a fraction on the top and the bottom by the same number, you're producing an equivalent fraction. So I'm going to do 30 times ln of 15 divided by the ln of 2. Ln of 2. And in this case, I'm going to get 117.26. So time equals 117.06. So in that case, voila. So there you go, Scarlett.